In this video, we're going to be looking at dependent events and also comparing them to independent events to see how we can see the difference between independent and dependent. Alright, so dependent events. These are two events, A and B, are dependent if the fact that A occurs does have an effect on the probability of B occurring. So an example of this would be taking a deck of cards, and in that deck of cards, we're going to be picking a card, then picking a second card, this is the important part, without replacing the first one. So the probability of A and B occurring will be the probability of A and B, just like always. And when it says and, we need to remember to multiply. But what we're going to do is find the probability of A, and we're going to multiply that by the probability, and the way we read this is B given that A already occurred. So multiplying the probability of A, then just multiplying by the probability of B, but because A already occurred, the probability of B changes a little bit. So let's take a look at an example here. Experiment 1. A jar contains 3 red, 5 green, 2 blue, and 6 yellow marbles. So it's the same jar as the one from the previous video, so that's a total of 16 marbles. If we choose a marble at random, and then we choose a second marble without replacing the first one, what is the probability of choosing a green and then yellow marble? So first we look at how many green marbles do we have. We have 5 greens, that's 5 out of 16. Now, if we took that green marble out of the jar and we didn't put it back, when we look at the probability of getting a yellow, there are still 6 yellow marbles. But now, because we took one of the green ones out, there are only 15 marbles in the jar. This is the part that changes. This one is what makes it dependent, because our total number is now changing because we've taken out that green marble and not put it back. So to get the final probability, all we have to do is multiply 5 over 16, that's the probability of green, times the probability of yellow. Remember, that line means given that the green has already been taken out, which we found to be 6 out of 15. So we multiply those, and we get 15 out of 240, and that simplifies to 1 over 16, which is approximately, or actually exactly, 0.625. So that is the first example. Let's look at a second example. Experiment 2. An aquarium contains 6 male goldfish and 4 female goldfish. You randomly select a fish from the tank. Do not replace it. I don't know what you're doing with that goldfish, but you didn't put it back. And then randomly select a second fish. What is the probability that both fish are male? So what we want to figure out is basically this. What's the probability of getting a male, and then, remember, and means multiply, getting a second male. So what we have to do is we have to find the probability of this first male, and the probability of the first male, multiply it by the probability of getting a second male, given that we already took a male fish out. So the probability of getting a male fish originally was 6 males out of the total, which, let's see, 6 plus 4 is 10 fish. Then we multiply that by the probability of getting a male, given that we already took a male out. So think about it. If we already took one fish out, there are only 9 fish left in the tank, and there are only 5 males left in the tank. So from there we multiply that out, and we get 30 over 90, which is simplified to 1/3, which is approximately 0.33. So we'd have a 33% chance of getting a male fish, not putting it back, reaching back in the tank, and getting another male fish. Experiment 3. Let's take a look. A random sample of parts coming off a machine is done by an inspector. He found that 5 out of 100 parts are bad on average. If he were to do a new sample, what is the probability that he picks a bad part and then picks another bad part if he doesn't replace the first? So we want the probability, we'll use B for bad part, of a bad part, and then getting another bad part without replacing the first one. So that's the probability of getting a bad one times, because it's and, the probability of getting a bad one given that we already picked a bad one. So the probability of getting a bad part, they said, was 5 out of 100. 5 out of 100. Probability of getting a bad part, given that we already chose a bad part, well, there are 99 things left since we took one out of the 100. And there are only 4 bad parts left because we already chose one of them in this first round. So now we simplify that, and that's going to be 20 over 9,900. That's going to simplify to 1 over 495, which then would equal about 0.002. So about 0.2% is the probability of getting a bad part and then getting another bad part. Again, all we did here was we took the two individual probabilities and multiplied them because it was one event happening after the other. Let's look at now the difference between this independent and dependent thing. We want to be able to determine, are these events independent or are they dependent, simply by knowing their probabilities. So let's take a look. So the way we can tell if two events are independent is we need to be able to show that one of these 3 equations here is true. If one of those equations is true, we can show that the two events are independent of each other. Now we really focus in on this equation here. The probability of A and B is equal to the probability of A times the probability of B. If that's true, that means the two events have to be independent of each other, meaning they don't have any effect on each other occurring. If that's not true, that means this probability of B is really the probability of B given A, and the probability of B occurring is affected by the probability of A. So let's take a look at an example of what that means. Again, all we have to do is show that one of those 3 equations is true to show that the events are independent, because those are the independent event equations. Experiment 1. We're going to label event G as taking a math class and event H as taking a science class. So G and H is the probability of taking a math class and a science class. So it says that the probability of G is 0.6 and the probability of H is 0.5 and the probability of G and H is 0.3. Are G and H independent of each other? So if we think about it, that means that the probability of math and science would have to be equal to the probability of math, and because it says and, we have to multiply, so times the probability of science. Now if that equation is true, then the two events are independent. So all I have to do is fill in the numbers here. Probability of G and H, they said, is 0.3, so that's 0.3. The probability of G was 0.6, and we multiply that by the probability of H, which was 0.5. All we have to do is show that is equal to 0.3. So 0.6 times 0.5, if we put that in a calculator, we will see that that is actually equal to 0.3. And then we just bring that down. So this is a true equation. So H and G are independent because that equation is true. Let's look at a second example. In a specific college class, 60% of students are female. So let's write that as a probability. Probability of female is 0.6. That's 60%. 50% of all students in the class have long hair. So let's do the probability of L for long hair is 50%. Okay. 45% of students are female and have long hair. So the probability of female and long hair is 0.45. 0.45. And this last one, of the female students, 75% have long hair. This one's a little weird. The way we'd write this, because we're just dealing with female students, that means we would say the long hair, given that they're a female student, is 0.75. So we know they're females, and of those females, 75% have long hair. All right, so question here is, are these two events independent or dependent of each other? So one way to do this is to use the independent equation that says the probability of F and L, or F intersect L, is equal to the probability of F times the probability of L. So we look F intersect L, that's going to be that 0.45. And we see, does that equal the probability of female, which is 0.6, times the probability of long hair, which is 0.5. So we multiply those two probabilities. We get that this side is 0.3, and then this side is 0.45. Those two things do not equal each other. So being female is dependent on having long hair. So what that means, doesn't mean if you are a female you have to have long hair. It just means that the probability of it occurring is more likely if you are a female versus if you are a male. Now, there's another way we can actually look at this problem. We can look at it this way. If we know the probability of long hair given that you're a female, which we do know, they told us that that was 0.75. If that probability was the same as just having long hair, which in this case was 0.5, if those two probabilities were the same, then we could say that they are independent of each other. But because these two probabilities are not the same, they're not equal to each other, we know right off the bat that these are dependent events. And that's because the probability of long hair given female was the same as the probability of long hair. That means that the fact that we're given that the person's a female doesn't affect the probability of them having long hair. Okay, in this case it does affect it, so that's why they are dependent events. All right, so that's the difference between independent and dependent events. So take a look at those practice problems, and good luck. Don't forget, if you have any questions, please reach out to your teacher and ask them. We're here to help.